In this work, we present an unsupervised framework for learning multi-object representations and visual dynamics. Goal-directed manipulation involves finding a sequence of actions to achieve a desired goal state. Our framework learns to manipulate a multi-object scene in two stages. First, we discovered unsupervised object-centric feature representations from RGB images. These representations, also known as slots, collectively describe the current state of the scene. And second, we utilize the discovered slots to learn multi-object dynamics and predict the future state of the scene after applying a pushing action. In summary, we introduce a novel unsupervised framework for learning goal-directed multi-object manipulation using only RGB images of a robot interacting with objects. The details of the two stages in our framework are as follows. In the first stage, we propose SlotTransport, a novel architecture that refines object-centric representation learning through slot attention. Using only RGB images, each slot learns to represent a specific element in the scene, including the objects, robot, and background. With SlotTransport, during training, slot features are transported across randomly sampled image pairs. This improves the learned representations and ensures each slot consistently represents a unique object. At every time step, we construct a graph representation of the scene. Here, nodes are the slots and edges correspond to their pairwise interactions. In the second stage, we introduce SlotGNN, a graph-based model for learning multi-object dynamics. SlotGNN predicts the future scene graph conditioned on the robot's action. Our graph-based model captures the interactions between the robot and objects, as well as the object-to-object interactions. Our framework can be used for model-based planning using only a goal image. Specifically, from the goal image, SlotTransport extracts the slot that describes the goal state of the scene. With this, we construct the goal graph. Using SlotGNN in model predictive control, we can then find an optimal sequence of actions to reach this goal. Here's an example of our framework in action, achieving a goal configuration from an initial state. Note that the goal state is only provided by an RGB image. The bottom row displays the slots identified from both the current and goal images using SlotTransport. Additionally, using SlotGNN's prediction, we highlight the optimal action with a green arrow. In this example, the objects are misplaced in the exact opposite positions. The robot efficiently moves each object back to its goal position while avoiding collisions between the objects. This example highlights how the robot leverages object-to-object interactions to effectively push both items together to their intended spots. In this next example, we see a scenario where the robot rotates the object to match the goal configuration. Given an initial image at t=0 and a sequence of robot's action, SlotGNN can roll out the learned dynamics several steps into the future. Predictions from our model are both stable and physically plausible. When using the same discovered slot, an MLP-based model is notably less accurate compared to our graph-based model. Furthermore, unsupervised keypoint-based dynamics prove to be unreliable due to inconsistencies in identifying object keypoints. We transfer our framework to the real world by collecting an additional 20 real demonstrations. This is only 5% of our simulated training dataset. SlotTransport successfully discovers accurate and temporally consistent slots from real images across diverse configuration and under occlusions. Even in unseen scenarios where some objects are missing from the scene, the discovered slots are consistent. We also demonstrate action planning in real world using SlotGNN's predictions. Given only a goal image, the robot rearranges the objects to match the goal configuration. This highlights the practicality of our framework, especially in real-world situations where obtaining ground truth object state information is not possible. Here's an example of a more dynamic scenario where a human constantly displaces the objects from their goal positions. and the robot comes up with a sequence of actions to push the objects back to their goal locations. Please visit our project page for more information. Thank you for watching.